In the modern era, innovators are discovering ways to make pre-existing tasks and methods more efficient. Others are jumping into new topics and finding a way to use the new material to our advantage in terms of the evolution of technology and education. The topic at hand is one that combines the interaction of light and mechanical motion. My name is Ruben Lopez from the University of Houston Clear Lake, and we will be taking a dive into a rapidly developing field of research known as optomechanics. The mentors, both from Texas A&M University, are Dr. Shofeng Lan, the overseer and head of this project, and Preston Kuna, current grad student in charge of leading this research topic. I would like to thank the OREU program, the Lan Research Group, and the Department of Energy National Nuclear Security Administration for funding the research and making this possible. The path of optomechanics brings plenty of groundbreaking ideas to light, some of which seem to be works of fiction. Plenty of research teams are currently working on such ideas and obtaining stunning results. The director of the UK National Quantum Technology Hub discovered a way to cool atoms to near absolute zero. The research of sensing gravitational waves is well underway and funded by the US National Science Foundation. This particular lab, stationed in Livingston, Louisiana, is one of the many laser interferometer gravitational wave observatories. A research team from Purdue University focused on levitated optomechanics, creating the world's fastest nanorotor and the world's most sensitive torque detector. In summary, optomechanics is the study of interaction of electromagnetic radiation with mechanical systems through radiation pressure or optical parts and devices. Our main objective for this summer is to model the relation between a mechanical node and optical node. Relating the two will develop a library of fundamental optomechanical simulations on which to build future complex optomechanical simulations such as bound state in the continuum, or BIC for short. Building a basis or foundation for these simulations will facilitate the construction of complex and detailed models for the research team and others who wish to pursue research of their own. Two sets of simulations will be completed and refined to obtain adequate results. The first set will model mechanical vibration response. The second will model optical cavity resonance. The final product will be a multi-physics simulation combining the two models. By combining the two, a direct correlation between the mechanical and optical cavity resonance is established, creating an optomechanical resonance model. The research team will be using COMSOL to run these simulations. With the use of COMSOL multi-physics software, one can create complex models incorporating various concepts in the world of physics, closely replicating situations that would work in the real world. The uniqueness of COMSOL relies on the effortless performance of calculations based on the user's inputs and choice of physical effects. One of the simulations was recreated based on pre-existing simulations provided by COMSOL to fulfill the optical portion of the study, the Fabry-Perot cavity simulation. The Fabry-Perot cavity simulation demonstrates how to find the resonant frequencies and the Q factor of a Fabry-Perot cavity. To do so, either an eigenfrequency model or a frequency domain model must be created. In the left figure, an eigenvalue transform point within the expected resonant frequency was manually inputted. The results show various solutions to the eigenvalue while also showing physical modes only. The table shown lists the resonant frequencies with their respective Q factors. The right figure illustrates the energy density within the cavity over a range of frequencies. This plot can be used to then find the Q factors given the resonant frequencies by the graph. Dividing the resonant frequencies by the full width at half maximum yields the Q factor. To view the radiation pressure from a mechanical perspective, a simulation for a generic loudspeaker was recreated. The availability of resources that pertain to our goals and studies are minimal, so the research team focuses on comparing pre-existing models, preferably ones that share similar properties as the models of interest. This simulation analyzed the acoustic radiation pattern using the boundary element method, or BEM for short. The results display the total acoustic pressure field in pascals on the left and the sound pressure level measured in decibels on the right, both residing in a three-dimensional domain. The loudspeaker is in an infinitely large room, so there are no interactions of any kind with other objects. The radiation pressure of sound waves is analogous to the radiation pressure of electromagnetic waves, so the simulation works as an adequate substitute for a propagating electromagnetic wave model. Ideally, The sound source will be changed to a light source, and the mechanical acoustic wave will be changed into an electromagnetic wave to revert to the initial goal. The Fabry-Perot cavity model demonstrates a hypothetical light source traveling through a cavity at different frequencies, whereas the loudspeaker model shows a source dispersing harmonic waves through an infinite space with no resonators or cavities to interact with. With these two pieces of information, the combination of the two will initiate the construction of the final product, the optomechanical model. A photonic crystal is used for this simulation as an optomechanical device to understand the interaction of light with various wavelengths flowing through the crystal. Waves within a specific frequency range are reflected, while those that pass through will propagate through the path created. The left figure plots the Z component of the electric field, revealing a propagating pattern along the path defined. The right figure shows the results of a wavelength increased by a factor of 1.3. In this case, the wave does not propagate through the path since the cutoff frequency prevents it from flowing. This is by far not the final product, but a stepping stone to further advance the research in optomechanics. The next step would be to build from this simulation by including an optomechanical device with a cavity to further study the light interaction within the device. Then replace the device with bound state in the continuum or BIC as mentioned earlier to create advanced and more complex models. The most common types of setups include nanobeams made by the same photonic crystals with cavities that enhance the intensity of the wave, a trapped and vibrating cold atom cloud or other levitated objects inside a cavity, a vibrating drum capacitor coupled to a microwave field, and many other possibilities. With the advancement made this summer, creating a simulation of at least one of these examples are well within our grasp. Thank you for your time.